Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello everybody. Welcome to another episode here at Master the NEC. My name is Paul Abernathy. As always, I'm your host for this podcast. Now, today we're going to talk about a topic that probably doesn't get talked about enough, because I think people want to get into the meat and potatoes of the code, but they don't go back and understand some of the things that we have to do in the code in order to eliminate unsafe conditions and why they're there. Again, one of the podcasts I did earlier talks about understanding the prescriptive requirements in the code and the performance requirements of the code, right? So go listen to that podcast, because I think that's really going to open your eyes up to what our whole intent here is when we're doing something with the National Electrical Code, what we're trying to achieve, right? So one of the topics is objectionable current, and because you can't see current, you obviously can feel it, but you can't see it, so you don't know what's going on. But we do get the symptoms of an improper installation. Elevated EMF is an example of a lot of potentially incorrect wiring schemes that people will utilize, and you can tell because you can get a higher level of EMF because we have an improper case to neutral downstream. We'll talk about that in a minute. But it also can be an unsafe condition where objectionable currents is anything to do with current that is traveling on an unattended path, and it was objectionable to the path that it should be traveling on. And so there's a lot of things that we do to prevent that, and we're pretty much charged by the National Electrical Code to arrange our systems in a way that we do prevent objectionable currents. Now, let's also be real. There is some installations where we're going to have the potential of objectionable current, and it should always be considered objectionable current, but there's a lot we can't do about it. But the code understands that if you have an objectionable path that might have an impedance or resistance that's so low that the majority of the current is traveling on its intended path, that it, yes, is objectionable current, but it's not at a level that raises the same level of concern. Whereas, for example, making an improper case to neutral in a panel that's in your basement, if you connect the grounded neutral conductor to the equipment grounding conductor in this case, then you're directly creating objectionable current, because now you're going to have current that's not only returning back on the neutral, back to the main panel, but it's now going to also be circulating through all of that metal non-current carrying parts that it shouldn't be traveling on, right? All those equipment grounding conductors, all those bonding jumpers that you have are now going to be carrying current that they're not supposed to carry current, right? And it creates a touch potential for somebody that comes involved in that system. So you create a hazard. Now, of course, also in a lot of systems, and we're seeing more of this today, people are hypersensitive to EMF. And so any type of improper case to neutral connection downstream can cause spikes in EMF, okay? And again, some people are hypersensitive to that. I'm not going to take that away from people because there are documented cases. About 10 years ago, I would have said it was kind of hokey. But sadly today, I have seen cases or been involved in some cases where I guess it's, some have been way out there, okay? I'm not going to lie. Some of them, the people are 10 feet away from the system, and they're saying they get burns on their body. And they're laying on a totally isolated bed for some reason. It might be just their 2-year-old with a Bic lighter or something while they're sleeping. I don't know. But what I'm saying is, there is a real situation where people are hypersensitive to EMF. It's kind of why you get that tingling feeling that somebody's watching you if you're in an area where it's a high elevated EMF and thing. Look, I'm not a scientist on that, but I'm just saying, for me as an electrician, when I get a level of high EMF in a milligauss, for example, then I know that there's a good chance that I have a lot of improper case to neutral connections. So when I do a little course and teach people about troubleshooting and things like that in buildings, again, a lot of commercial buildings, they have to have insurances to keep their tenants safe. And if their old building is poor wiring, energizing metal parts and things that are not supposed to be energized and all this type of thing creates circulating current, which can be a hazardous condition. We can use milligauss, for example, to be able to ferret out where there might be an improper case to neutral. That's just one technique to use. They're fairly inexpensive devices. it's not a 100% hit all the time, but it does give you an idea if there's a lot of incorrect case to neutrals. We had one situation where we had a hallway that started out because a person went out and bought their own milligals, and they did it because they saw some documentary on TV. Anyway, it was really, really high. And they asked us to come in and look at it, and of course it was really crazily high. There were people that were reporting headaches and things like that in the building or whatnot. Again, people can be hypersensitive to it. And anyway, the entire lighting system had an improper case to neutrals. Means the equipment grounded conductors were connected to the grounded neutral conductor at every one of the luminaires within the actual hall. And there was literally hundreds all. And it created such high magnetic fields that it was just incredible. And a simple fix was to go through and fix all those luminaires. And it was amazing what it did. And the complaints actually stopped. So I don't think it was just the tenants wanting to make the landlords do a bunch of work and spend a bunch of money. There was a concern there, and that was a direct example of alleviating an issue that people had. Now, the owner, had to pay the bill, but the peace of mind that they got after that was, and a plus with improper case to neutral connections, you do create the potential path for current to travel on unintended paths, and that can be a consequence because we know people get shocked because of differences of potential. And if you provide a path for current to flow back to the source, by gosh, it's going to travel that way because current takes all available paths, not just the path of least resistance. It takes all available paths that are there that will complete that circuit. Now, with that said, that's going to give us some good, helpful explanation when we get to something here in a few minutes. But let's talk a little bit more about objectionable current. Now, what is it? Now, remember, grounding electroconductors, equipment grounding conductors, they're not intended to carry current under normal electrical system operation, okay? They're not. They're only there for things like ground fault. Now, what happens is objectionable current, or at least one source of objectionable current, occurs when the system's neutral conductor is grounded improperly downstream from the service equipment. So there's a reason why we run 4 conductors to a remote distribution panel. There's a reason why today we run 4 wires to a range or a dryer, okay? There's a reason why we do these things. We want the intended path for current to take to be on that path that it was intended to take, okay? If it accidentally has a ground fault over 2 metal paths, then it has a path to get back to clear an overcurrent protected device and shut that system down. But it's not going to take that path intentionally. It's under a ground fault condition. So anything that would travel on the equipment grounding conductors and things like that are not the normal intended path under normal operation, then it's going to be objectionable current, okay? Now, we're not talking about the current that travels on equipment grounding conductors, for example, in a ground fault condition. That's a short amount of time, and it's designed that way because table 250.122 for equipment grounding conductors, it does not size the conductors based on their continuous current rating. It bases it on their short time current rating. For example, a 14-gauge copper can carry thousands of amps of current for a short amount of time. And let me tell you, overcurrent protected devices will trip in about 1/5 the time of an airbag in a car. And again, if you blink, an airbag's already out. So that's how quick these devices are designed to operate. So there's no way that you're going to allow the current to travel on an equipment grounding conductor in a ground fault condition that's going to get the temperature high enough to damage any insulation that might have a rating of 75 degrees C or even 90 degrees C because it's going to operate so quickly. For example, a 500 amp overcurrent protected device under 250.122 says that for that 500 amp device, then you would use a 2-gauge copper. Well, a 2-gauge copper is only good for 115 amperes, so there's no way that we're sizing equipment grounding conductors based on its current carrying capacity, right? We're sizing it based on its short time current rating capacity, which can be astronomical for short amounts of time. You wouldn't believe the amount of current that a copper conductor or even aluminum conductor can handle in a short amount of time, right? So that's what we're banking on, and that's why it's so important to make these connections properly. So that's kind of an example of what we do it. So some people come to me and say, well, Paul, how in the world could we put a 2-gauge on a 500 amp overcurrent device? Because you're not putting it on the device. You're putting it on the path for ground fault current. And it's going to happen so quickly that it's not going to have any effect on the insulation at all, okay? So that's kind of the concepts to kind of help you understand it. Now, The other thing to remember that 2 gauge is only about 23% of the rating of the overcurrent device that it's terminating to, which in this case was a 500, which is protecting it, which is a 500 amp overcurrent device. So that 2 gauge is about 23% of the rating of that overcurrent device. Okay, you have to understand the difference between short time current ratings and the continuous current ratings, because the ampacities that are given to us in 310.15b16 for the 2017 code or 310.16 for the 2020 code, that's based on a continuous current rating. Again, yes, as long as you have no more than 3 current carrying conductors and the temperature is 30 degrees C or 86 degrees Fahrenheit, that's a perfect world, then that is what that conductor can carry without violating the insulation's rating, right? Now, because we don't live in a perfect world, we have ambient temperatures that are higher than 30 degrees C, or we have raceways that carry more than 3 current carrying conductors. Well, that heat's got to be dissipated somehow. And so ultimately we do what's called derating, adjustment and correction, in order to lower the amount of current that's going to be traveling on that conductor, because the flow of current or the reaction to the flow of current creates heat, and it could raise the temperature up in that conductor that could be volatile to that insulation's rating. Okay, now you put a bunch of conductors in a raceway, then it's enclosed in that annular space, then heat can't get out. And if heat can't get out, then it's going to play a role on rise of temperature and potentially damaging that insulation. And that's what we're trying to not do, right? So all these things work together in a great harmony. It's important that you understand them because it really can serve you well as you move through your career. Now, let's talk about objectionable current in another way. Another way that you could have objectionable current is this. Now, let's talk about current flow. Now, I could have a situation where I have a main panel in a building, and I'm going to feed separate panels and remote distribution, okay? So I have 2 buildings, let's say, and I'm feeding a feeder to one building, and I'm taking a feeder to another building. It's all one same electrical system. It's under single management, if you will. And so I'm taking a feeder to building A and a feeder to building B. Now, at those buildings, since they are detached structures, you and I both know that requires a grounding electrode system. So we have 4 conductors that go out to a panel that's located in that building, and we have to have a grounding electrode system. Now, that grounding electrode system will have its own grounding electrode conductor from the electrode that goes up to that panel that connects to the equipment grounding conductor that we ran in those 4-wire feeder. The neutral is isolated from the enclosure, and that's what we create this isolation of the grounded neutral conductor, because that is the path for return current back to the source, which is back in the main panel. Now, the problem happens is that since we have those equipment grounding conductors that run from the service to those remote buildings, and it connects to the grounding electrode conductor that goes down into the earth, and we know earth is not to be used as a return path. However, remember that basic concept that we learned early on in electricity is that electricity in the current takes all available path, not just the path of least resistance. So while the earth is a return path back to the source, which is the utility transformer, either at the substation or local pad mount transformer for the neighborhood or whatnot, that's a common location to the neighborhood. So current will travel through the earth. Again, it's because of the impedance, the amount is low, and the majority of that current is going to travel back on the neutral like it's supposed to. But simply for the fact that current will travel back through the grounding electrode system back to the source means that is also considered objectionable current. Now, it's kind of hard to remove that because it's all part of the same electrical system, but here's the kind of concept of how it flows so you kind of get a visual picture. So I've got a main panel in my building A, or my main building, and I'm taking a feeder to building A, and I'm taking a feeder to building B. And I've got them running 4 wires. So at that panel, I've got 4 conductors, I got a panel, I got a neutral bus that's isolated away from the enclosure, and then of course I got equipment ground, and then from that equipment ground that connects to that grounding bus over to the grounding electrode conductor down to the electrodes, let's say in this case ground rods, if you will. Now, when the current is drawn on that building, it goes from the main panel into building A, down through the various breakers, out to the loads, back to the neutral, and back to the source, back to the main panel, and of course back to the transformer. Now, because at the main panel, that grounded conductor and the equipment grounding conductor is connected also to the grounding electrode conductor to that main building's electrode system, current will also return back to those remote buildings through the equipment grounding conductor, down those grounding electrode conductors, into the electrode, into the earth, and back to the actual transformer to complete that circuit. You can't stop that from happening, okay? It's just the nature of how it happens, because that is an available path back to the source. Now, because the earth is such high impedance, I should say, is that the amount of current that's going to travel is very proportionally low. And so it ends up being negligible in most cases. But for all intents and purposes, that is still considered objectionable current. It's just, how do we try to eliminate as much objectionable current as possible? Make those connections properly where necessary. Don't intentionally put current on a path to get back to the source. Don't put the neutral in parallel when you don't need to, because again, it's not in parallel with the return current from those panels. It's actually the current that's going back to those remote buildings down to the earth and back, and that's not the same thing. So it's just one of those things you have to understand, that you're not going to get rid of everything, but one of the ways that we can keep from having objectionable current is that let's stop making those improper case to neutrals at those remote distribution panels. Stop running 3 wires to panels. Stop running 3 wires to ranges and dryers, which we already know that the code doesn't allow us to do now, but and we're not talking about things that are required under existing rules in 250.32. We're not talking about that. We're talking about new installations, okay? We're trying to make things safer from a certain point on, and that's why we've done it. So if we make an attempt to separate in junction boxes, that we really push those equipment grounds back in the box after we make everything up, so that when we're pushing in the grounded neutral conductors, if they're spliced, that we don't take too much insulation off so that bare could come in contact with the equipment grounds. We do everything right. We cover all that exposed conductive material. We push those boxes back in there, and the devices back in there. With luminaires, we do the same thing. We don't do bootlegging. There's a lot of people out there that want to cut shortcuts, and they will bootleg, because again, we know that the equipment grounding conductor and the grounding conductor both go back to the main panel and they connect at the same location. So some people say, well, what's the harm? I'll just use it. Well, because it is uninsulated in most cases, in most normal, let's say, dwelling residential applications, then you know what? You impose current onto the equipment grounding conductor where it's unsafe, okay? Now, if you do that in commercial buildings where you have insulated equipment grounding conductors, you also remember that we also have bonding jumpers that are going over to metal enclosures and over to equipment. So you're going to put current on a return path that it's not intended to be, and thus you could elevate the touch potential on other metal products that are involved in the electrical system. And we don't want to do that. It creates a hazard. Okay? Now, so that's kind of the concepts of what we're trying to do to prevent it. Just do things properly and learn the concepts of 250.6, understand A and B, to how to arrange to prevent objectionable current, and how to come up with an alternative to stop objectionable current. That's kind of the focus of what we want to talk about. Now, the code goes on to tell us there are ways that we can alleviate or stop objectionable current. The one thing we have to remember is that we can't lose sight of the principal core reasons that we had an effective low impedance ground fault current path. So we can do different things, and the code's going to tell us that we could disconnect one or more, but not all of the grounding connections if necessary. You got to do a little investigation as an electrician to determine what's the best course of action. But you can't remove anything that's going to affect that conductive low impedance return path that's so vital to overcurrent devices operating and keeping systems safe. So you really have to, this is where you get paid the big bucks. You have to understand systems. Now, I get a lot of calls from people when they have issues and they don't understand how to get rid of this stuff, and I'll go out and help them, or I'll talk them over the phone because they just can't figure out how to get rid of this objectionable current that's causing problems. Well, there are solutions. You just have to look at them. You can't just remove all the connections and create a hazard alone, because there's certain things you can do. Now, you might be able to change the locations of the grounding connections at another location or another method that might remove the condition or reduce the condition. Or, for example, you could have a situation where you have luminaires, like my example, where you would separate the accidental contact between the grounded and the grounding conductors, and you alleviate that objectionable current. That might be one of the methods. The key is you don't want to interrupt the continuity of the conductors that are part of that return path that's so vital to clear things like overcurrent devices or tie all metal parts together. So you have to really think about it. The code will give you some alternatives to stopping objectionable current, but you really have to think about what you're doing before you just start pulling connections loose and things like that, okay? You can take something that was mildly unsafe and turn it into a vastly more unsafe condition by not knowing what you're doing, right? So I just can't stress enough that you do have some rules in the code which will kind of allow you to do certain things to try to stop it. Just please remember, you cannot reduce the effective ground fault current path that is required by 250.4A5 for grounded systems or 250.4B4 for ungrounded systems. You can do certain things to try to alleviate this objectionable current. Better yet, install the system right in the first place. But you cannot eliminate or change that effective ground fault current path in any way. You can't reduce its effectiveness. And that's the real key I want to hammer home with that.